So this webinar, since you guys are going to have a final exam, what I thought is to have a review of everything we have seen so far. And if for those who might be a little bit behind, this will be a chance to catch up, hitting on some key issues. And so what I like to do here is to always be attentive to see if there is any question, and please ask questions on the topic I'm discussing or some other topic. This is the best chance to do it. And if there are a few questions, I have some things. I have some things prepared, so I'll start going with that. But I have no problem in addressing questions that you might have, that you let us know through the chat, or questions that that relate to what we are talking about. And in addition, to encourage this, I will ask you questions every once in a while, because the answers are anonymous. Feel free to click what you think is right, or always A or always B, whatever you think might be. Will get us discussing things that there is a chance that are not always as clear as you'd like to have them in your head when you're troubleshooting the plan. So in our first slide, we have the schematic of the SIM treatment equipment. Let's see here. And we have the inductors. In this case, we would have 3 inductors. Some plants have 2, some plants have 4. And below, we have this other schematic of temperature as a function of the distance, right? And we have starting temperature coming out of welding, and hot, and then it cools down a bit, and hot after a second inductor, then we reach a peak temperature and cools down until it reaches the quenching cage, right? So I want to open a poll here and ask you a question, because what I said sounds like it makes all sense. But let's get a little bit more concrete. Is what is this temperature represented in the curve? We say the temperature. Okay, is that the average temperature in the whole cross-section of the tube? Or is it the average temperature in the cross-section of just the bead? Or is it the maximum temperature in the cross-section of the bead? What is it? Oh, and I think I'm having some answers here. Let's see. All right, great. Wow, this is going awesome. All right, so, wow. All right, so I think we're doing very well with this. Let's give it one more minute. All right, I'm about to close, so if any of you have the finger hovering over a button to click, this is the moment. All right, so I'm gonna close it there. All right, so now everybody should see the results, and the results that have most people, the answer that most people chose was that it's a maximum temperature in the cross section of the bead, and that is correct, because that's the parameter is measuring just the temperature on the outside of the let's see, on the outside of the tube, and the outside is the hottest part. So this graph we measure here, and I'm moving my laser pointer over it, represents the maximum temperature in the seam which means sometimes it's a conservative measurement, and for example, in the quenching cage, and sometimes it's a very non-conservative measurement, and we have to account for the temperature differences between the inner and outer diameter, and we'll talk some more about that. Now, I intentionally chose potential answers that were somewhat similar. We have some choices as the average temperature in the cross-section of the bead. And that answer is an interesting one because as we're going to see when we calculate inductor power, we're using an average temperature, right? But, and I'm going to highlight on that when the time comes. But what is important to keep in mind is that every measurement we have, and this is a very specific research and scientific measurement we do, every other measurement we'll have in a plant of industrial relevance is going to be on the outside of the tube, and it's always going to be a maximum. Everything else can only be lower. Now, we also have a choice of first question, that is average temperature in the cross-section of the tube. That one I want to dwell on this for a second, and is when we look at the cross-section of the tube, the hot part is only the seam part. Even in small diameter tubes, in which the temperature tends to distribute quite a bit, still the bead is much hotter than the rest of the tube. So it's important to keep in mind that as we talk about temperatures, typically we are talking about temperature of the bead. There is one exception, that is the temperature I call the TI, and I'm going to refer to soon. That is a temperature we use when we calculate cooling rate during the air cooling regime, right? But other than that temperature, we are always talking about temperature of the bead, and I'm going to say clearly when we are not. So thanks a lot for these responses. This makes it a lot more interactive, and I'm super glad to see that we're pretty much the vast majority are on the same page. So it's the order same temperature, and I want to highlight here that in a graph like this, we get to see the inductor length. So if this is the inductor length for each inductor, we would see it reflected here, right, in the axis. Then we have the distance between inductors. That is something we have discussed in the course, and I'm going to review briefly later today. And we have this distance between inductors, and we see this cooling here. And we have discussed quite a bit about that. We have an air cooling length. That is the distance between the end of the last inductor and the beginning of the water cooling cage. Clearly, this drawing is not to scale, but this air cooling length is actually where everything happens, and where we get the right properties for our seam. We have the water quenching here, the water cooling cage. Before the inductors, we have our welding stage that we don't have indicated here. That would be before the inductors, and there are two important temperatures here. There are many intermediate temperatures, H1, C1, H2, C2. But this peak temperature is especially important, as we have discussed, is when we reach full austenization through the whole bead. That's the key thing. And the other important temperature is the quenching temperature, in which we should have already exhausted all transformations. We should have no possibility of transforming to martensite or to hard faces. So all the transformations should be completed, and if there is any residual austenite, it's an austenite that will not turn into martensite. So this temperature, we know we need to be below this temperature before we quench at anywhere in the cross-section. So with this, we set the stage to have like a holistic view, a complete view of our seam heat treatment process. Right, and so now, let's see here. Let's do another poll. When we talk about the temperature at TS, right? I'd like to discuss a little bit more about what this is and have some sense. So the poll is going on, and let's see what you guys think. And as you guys are answering, I want to highlight that this is about reality. It's not so clearly defined as mathematics. Sometimes in mathematics we have a one and only answer, and that's it. And in this case, I'm intentionally bringing up questions that will require some qualifications. So don't worry about things being just right or wrong. Hmm? You guys rock. This is great. This is going fantastic. All right, we have I think only one missing. So I think I will close the poll here and show you your answer. And so this is fantastic. If you get to see your answers, we have split more or less 50-50 the choices between the whole cross section of the bead or only the outer surface of the bead. And this is an important thing to discuss. Both are right. This is the story. When we come out of welding, the temperature distribution through the weld thickness is fairly uniform because welding is through the thickness. It's not coming just through the surface. So it is the outer surface of the bead, and it is also representative of the whole cross-section in this case. When we come out of the weld, the temperature we are measuring on the outside, this temperature at point S, is fairly representative of the average. Of course, nothing is ever going to be exact, but this is fairly representative of the average. And it's a good thing to know because our calculations of inductor power are based on average temperatures. Now, nobody picked the whole cross-section of the tube, and I think it's the right choice. However, it's important to keep this in mind, that smaller cross-section tubes, smaller diameter tubes, will tend to come hotter out of the welding stage than big diameter tubes. And the reason is during the welding process and in the distance it takes to go from welding to the first inductor, the heat is going to distribute a little bit, and in small diameter tubes, the part of the tube that is opposite to the weld is going to be warmer than in the big diameter tubes. So I think this is going super well, and thanks again for the very fast participation. It's good, excellent. So I think so far we're all on the same page.
Patricio?
Yes. Yes.
I would like to make a comment about this temperature because, well, I'm a bit delayed with the course, but I'm now week 3, and I was working with the minimum length to cool. And I was a bit surprised because we have always made a lot of suppositions about this temperature, and everybody is like a bit, I don't know how to say, but relaxed about this temperature that is around 200. But I make the numbers changing this temperature from 100 to 200, and it's a lot. It's very big the difference between the distance using a temperature of 100 Celsius degree than using a temperature of 200 Celsius degree. For sure, to have a 200 Celsius degree temperature, as an average between the welding and the room temperature, means that we should have 400 Celsius degrees before the first inductor. In my opinion, I don't believe that we have this temperature before the first inductor. But we are not very get used to check this temperature. So I would like that my companions try to measure this temperature on their lines to see which is this temperature. Because using 100 Celsius degrees gives us a minimum length of 20 meters, but using a temperature of 200 Celsius degrees gives us a length of 47 meters, which is more than the double. So if we use 150 Celsius degrees, this distance goes down to 29 meters. So I will be a bit worried about this temperature, and I would like to check it.
Okay, so Deborah, thanks a lot for the contribution. Let me see if I can rephrase it, and I'll tell you what I think about what you said. So what I think you said is, if with the formulas we have, and perhaps even the model, you get that depending on your choice of your temperature at this point, the starting temperature or the intermediate temperature we talked about for cooling during the air cooling stage, the TI that I'm going to dwell that on more that later. You said the differences are very big. You come to the conclusion that the length for cooling can vary a lot, including sometimes being longer than the what you have available. Did I capture what your question was?
Yes, that was my question, because some lines have an UT equipment before the first inductor, so they cool the well, but not all the lines have the UT. So I have some doubts about this temperature now, and I would like to know which are the temperatures of all the lines that we have in Tenerife.
Okay, so and so what you added now is that before the first inductor, you have a UT section, which would mean that you have to be below 100, right?
Yes.
Okay, so let me give you some feedback on this. Number one, these formulas are not perfect or not exact. For perfect or exact, you either do an experiment or you have this model from CINI. But what these formulas are telling is important. You have identified a parameter that is to which the process is very sensitive to that parameter. That is an important piece of insight. Now, something interesting is you identify, and I agree, it's a very sensitive parameter, and you seldom measure it. For example, now you mentioned you have circumstantial evidence that this temperature should be below 100 degrees, right? I actually don't know what this temperature would be, and my first conversations with Eduardo, he was mentioning higher temperatures, and in retrospect, I think he was mentioning only the seam and for some product, not for all of them. So when I suggested something like 200 degrees, let's agree that it was an informed choice and perhaps not so well informed. But what matters here is that if we think it is an important parameter, maybe we can make a little bit of an effort to measure it. I do agree that is very sensitive. I had seen that myself, and I will tell you guys why that is sensitive. The reason is when you're in the air cooling stage, the heat goes out of the seam and out into the rest of the tube. So if the tube is cold, the heat moves faster away from the seam. If the whole cross section of the tube is hot, it moves slower. In typical welding operations, people use that to control the cooling rate and control the hardness of a weld. In your case, that can get you into trouble if you cannot transform fully before the quenching stage. So, Deborah, I agree with you that this starting temperature or the intermediate temperature here make big changes in the process. We don't have reliable measurements of this, and it's possible that the guesses I have were not the best. My suggestion would be measure one or two, not necessarily to do a line measurement, but measure it once or twice to have a sense of what we're talking about. S is at the seam, but the TI, that is the one doing the air cooling rate, that would be in the opposite end of the seam, right? To some extent would relate to this, but it's in the opposite end of the seam. Deborah, does that more or less answer your question?
Yes, it's just that I would like to make this comment because it's surprised to me that the formula and the influence of this temperature. That's
yes.
all that we didn't take too much this temperature into account too much. That's why I was a bit surprised and just want to make the comment.
And thank you. Identifying sensitive parameters, I think, is one of the most important things, because beyond modeling, you at least know what knob or what thing is might be having a big effect. Okay, so if you guys, I'm gonna keep moving, but if there's any more question about this, please bring it up. I have no problem going back. And I think everybody benefits from a general conversation. So a little bit about how the heat moves in the pipe wall, right? And I'm bringing this up to set the stage and enhance our intuition about how what things to look for. So we have three mechanisms in heat transfer in the pipe wall. In this slide we have here, I'm discussing the first one, and it is conduction across the wall thickness. That means during the heating stage in the inductor, the outer part of the seam is hotter than the inner part of the seam, and that is due in part to the it's due in part to the effect of the magnetic effect of the tube that it has a skin effect. And if we have a full electrical reference depth that covers the whole thickness, still in the outer surface of the tube, just being closer to the inductor, it's going to get it hotter. So the outside is always hotter, whether it's skin effect or proximity to the inductor. Now, when we are in the air cooling stage, we have enough time to make this section fairly homogeneous. So during the air cooling stage, homogeneity across the thickness of across the wall of the tube is not so much of a big deal, but the cooling happens with the heat that goes from the seam to the other parts of the tube. That's why it is important to have a sense what is the temperature of the tube far from the seam, and that is the issue that Deborah was raising. And there is another heat transfer mechanism that is not so much within the wall, but from the wall to the outside. We have convection, we have radiation. The radiation goes to the outside. Radiation can go from the seam, the hot seam, into the colder part of the tube opposite through the inside of the tube. But although these are present and they exist and they make a difference, this mechanism of convection and radiation, they are secondary compared to the other two mechanisms we discussed before as going out in the circumferential direction or going out through the thickness. So as we talk about the heat moving through the thickness, right? There is something that is fairly established in the heat transfer community, and people call it characteristic distance of heat transfer. It has many names, but in analogy with the electrical reference depth that is often used in induction heating, I name this a thermal reference depth. And in the course, we have discussed in quite a bit of detail about the subtleties of thermal versus electrical reference depth. So in this thermal reference depth that you get to see in the slide, we have this formula. Let's not worry about Greek letters, whatever we call it. It's the distance that the heat moves by conduction. And it has a very simple formula that comes from very fundamental principles, which I have skipped, but I would love ever to get into more detail. But this very simple formula says that the longer the distance into the mill that we talk, right? Distance correlates with time, right? It takes some time to move a given distance in the mill. The bigger the length makes a bigger thermal reference depth because it gives it more time. Conversely, the higher the velocity for a given length gives us less time of residence. So the higher the velocity, the smaller the thermal reference depth. And it's not linear, it's related with this formula here. And so on that note, since you have this formula, how about if I open a poll and we can see if we can make a prediction. This would not be the first time I ask you to do such a prediction. However, from feedback in about the course, the quantitative exercises, people answered faster and more easily the qualitative exercises than the quantitative. So I opened up this one and see what we if we feel it's difficult, we can do this together now. This is going well. Thank you very much, guys. Keep it coming. I know that for this one, we need to go back to our calculator. If you want to see the formula again, we have it here. All right, this is going fantastic. I'm going to give a couple more, 10 more seconds in case anybody just getting the last results from the calculator. All right. So, so I think you all would have seen the results. And we're on the money. This is awesome. Thank you. We all agree, and this is not such an open-ended question. In this case, it moves the way it moves, and there's not a whole lot to discuss. So in this case, if we apply the formula, you might have gotten this 9.6 millimeters, which sounds very accurate, but don't be fooled, right? And now something interesting about this result is that in this confab F1 line, the maximum wall thickness is 13 millimeters. So heat conduction alone is not going to be enough to get a uniform wall temperature. And that's an interesting thing to keep in mind. Sometimes it is, sometimes it isn't. If heat transfer enough is not if heat transfer alone is not enough, then we need to bank on the electrical reference depth. We have to make sure that the electrical reference depth covers the whole thickness of the tube. One or the other has to cover everything. Otherwise, we would have that the outer surface of the tube is much hotter than the inner surface at the part of the seam. So this simple exercise, and it's such a simple formula, actually helps us think. Please don't believe that these numbers are perfect or magical, but these numbers, they do help us think, and that is what is important, and they bring issues to our attention as Deborah mentioned before, right? So if we were limited by our thermal reference depth, for example, if the electrical reference depth was also smaller than the thickness of the tube, that means we have to reduce the mill speed such that to give more time, more residence time for heat to propagate, and the thermal reference depth would increase. All these things are good to keep in mind. It's not about the math, but about having this intuition about how the variables play. And although we all knew that with bigger distance or smaller velocity, things start to get better, the heat propagates. For example, we see that it's not proportional. We have this other effect that means a 20% decrease in velocity would buy us only a 10% increase in thickness. That's the way a square root works, right? And this is also the reason why the inductors are sized 200 kilowatt per foot, because if you put all the kilowatts all at the same time, you're not giving time for the heat to propagate, and you would end up like overheating the outer surface of the tube. Okay, thank you very much again. This is going very well. Well, I think I already answered this question, but since I did, let's see, because we have it prepared, I'm going to do it quickly. So, can we have an answer? Is this thermal reference depth enough for a uniform temperature? This one better get another 100% score. All right. I close in a couple of seconds here. Oh, again, thank you for the participation. This poll system works really well, really well. Okay, so I'm gonna close and share the results. And so almost all of us agree that if the thermal reference depth is about of the order of 10 millimeters, and we have a wall thickness of 13, this is not enough in its own. It's not enough in its own on its own to give us a uniform temperature in the cross section. Yes, we can make a good product in this condition if we have enough electrical reference depth. So that will be important to keep in mind, that heat transfer alone is not good enough in this case, and we can move on to the next thing, that is the electrical reference depth. So we're going to check on that. So electrical reference depth is how deep into the wall the induction heating goes. And there is something funny about electromagnetism, that you put that if you try to bring this electrical heating on a surface, it creates currents that counterbalance it. So it's very difficult to get penetration. And this will also, this issue of self-shielding, that is called the skin effect, is magnified by the magnetic properties of iron. So something interesting about iron is that it's magnetic at up to about more or less 760 degrees C. I'm giving you a sharp number. It's a lot more diffuse than that, but this is a good ballpark to have an idea. And so if we are below 760 degrees C, the steel is magnetic and gives us lots of shielding. And again, let's not worry about Greek letters, but let's remember that the electrical reference depth is inversely proportional to the square root of the frequency, and it's very small for when the steel is magnetic, and it's larger when the steel is non-magnetic. There is a factor of 10. It's a big thing. So I think as we approach to the break, I think we have one more poll to bring up and help us discuss. So here's my question. How does the electrical reference depth vary across inductors? So we have the first, the second, the third, fourth, however many inductors. Is the electrical reference depth smaller at the beginning and bigger at the end? Is it the opposite? Is bigger at the beginning and smaller at the end? Is it more or less the same for all inductors? Let's see. All right, I will close the poll in a couple of seconds, just in case you're debating. All right. Right. So, well, I can tell you that this course is going very well because we have a complete agreement. The first inductor, we're going to have is much smaller electrical penetration, electrical reference depth. And that's very important because what this means is that the outer surface of that during the first inductor, the outer surface is going to be a lot hotter, right? The inside, and we have to live with this. Now, thank God, because we're starting at lower temperatures, we don't have a risk of melting, or the risk is lower, and also we are far from reaching the peak temperature that is the one we really, really care about. So this is again important to keep in mind about the effect of about the effect of magnetization in the tube, how it varies with temperature. All right, I think we can do one more poll here, and that would be. Now let's get a little bit quantitative. We have this formula, and how does the induction heating penetrate using in the inductors of confab F1 line? So the frequency at confab is 1 kilohertz. If you want to see the formula again, we have it here. 1 kilohertz frequency. All right. So to make sure we have some time to discuss it, I'm about to close the poll. So if you guys want to click your suggestions. All right. We'll close. Okay. All right, great. So what do we get? We have like again a fairly even split between B, that is 1.6 millimeters, and C, 16 millimeters. And so actually the real answer to this question is not A, B, or C, right? This actually is, what inductor are you talking about? If you assume I'm talking about the first inductor, the right response is B, right? Because the first inductor is cold, the steam at the first inductor is cold, and the electrical reference depth is very small. If you are thinking about the last inductor, the one that gives us a peak temperature, by then we are in the austenitic regime. We have the steel is non-magnetic, and the electrical reference depth becomes much bigger, a factor of 10, 16 millimeters. And so both B and C are correct answers. But the important thing to keep in mind is which inductor we're talking about. The answer A of 0.16 millimeters, that is unlikely to happen. So I did a little bit of a survey, and this will be my parting slide before the break. I did a survey with data that Deborah Tieppo gave me from Tenaris Mill. And if you look at different mills and different lines, this is the this column has the frequency that they would have. It goes between 1 kilohertz and 3 kilohertz, right? And the electrical reference depth for the non-magnetic part, that means when the tube wall is hot, the one that would give us the peak temperature, we calculated using the formula, this exact formula you have, and I compared it with the maximum wall thickness of the mill. And what do we see? That, for example, at confab F1, the electrical reference depth is bigger than the wall thickness. That means even if I don't have the heat conduction across the wall, I'm going to get a relatively uniform wall temperature. But conversely, if we look at Conroe, mill number 3, the electrical reference depth is smaller than the wall thickness. It's not a huge difference, but what this means is that in this case, changing the mill speed would affect what it means is, in this case, we need heat conduction to homogenize the surface, the cross-section. And if we depend on heat conduction, the residence time is relevant, and if the mill moves faster, it can get us into trouble, but because we need the heat conduction to help us reach this other end of the tube. So if you have any questions that come up either right now or during the break, you can put it in the chat, and we'll address them all when we continue. So we talked about some key temperatures, and we talked about what they meant. We talked about how when we heat, we have we have to reach the complete wall of the tube, whether it's and it is we reach through thermal conduction or through directly putting the electrical heat there. We discussed all those things. Now, an important question is, what is the minimum inductor power, right? Or what power should we give to our inductor? So we discussed in the class a way of calculating this, right? And the slides that you had in the class are a lot more clear than this one, but I think we'll make sense out of this anyway. Here it says that the heat we put in watts is a factor of 5 times the thickness, the wall thickness, times the width of the temperate zone, and times the mill speed, and times TH minus TC, where TH is the average temperature in the treated area after induction heating, right? So this would be the average temperature in the cross section of the bead, right at where we have the peak temperature. So what is TC then? And the reason I'm asking this is because I think I haven't been as clear as I would have liked to be before. So this will be my opportunity to clarify myself. What is TC in the calculation of minimum inductor power? All right. So I'm going to close the poll to discuss the results we got so far. And we have one coming in progress. I'm sorry about that. I didn't see one in progress, and it will be a quick answer. All right. So let me share with you the poll results. So most of you suggested that the TC is the average temperature of the steam entering the inductor. That is what TC means in this equation. So I want to be very clear that when we calculate inductor power, the inductor power is essentially based on how much heat we had when we came into the inductor, how much heat we had when we came out of the inductor, right? Or what if we're talking about total inductor power, is how much heat what temperature we had coming into the first inductor and how much temperature we had coming out of the last inductor. And however, some of you said it's the quench temperature, and of course, this is not the right answer in this case, but I have said elsewhere that TC was the quench temperature. Notation is never easy. What I want to highlight here in this slide is I have used the name TC for two things that are different. And I apologize for that, but that's what we have right now. And as long as we have clear in our mind is that when we talk about inductor power, it relates to temperature coming in and temperature coming out of the inductor. But when we talk about the quenching temperature, we also have called it TC, and eventually we might come up with a smarter naming scheme. And that is the quench temperature, but it applies for these other problems in which we're talking about quenching, not the problems in which we're talking about just reaching the peak temperature. So thanks a lot for answering this, and I hope this ambiguous notation is not going to bring much confusion as you do the exercises or as you discuss things in practice in real life. Okay, so here we have the average temperature and treated heat area before. I'd like to ask you now a more of a quantitative question, which I think, seeing how we have gone so far, I'm feeling confident about all these things. These are questions we have discussed before, and these are questions that are in the final exam, right? Estimate the minimum inductor power for a particular case. In this case, I'm using as an example the Hickman mill number 6, and considering a wall thickness of 9.5 millimeters. I'm giving you the mill speed, both in the units that you might be more familiar with in meters per minute, and in meters per second, that is the units that are in the formulas. If we assume a peak temperature, right, that a target peak means anywhere in the steam we should reach these 900 degrees, right? And let's say that when we get into the inductor, we have already a difference of 200 degrees, and sorry, that when you come out of the inductor, it's 200 degrees C, and when you come into the inductor, you have 100 degrees C of difference. The width of the temperature zone is 22 millimeters. So to be clear, the temperature difference when we come in is homogeneous 100 degrees, coming out of the welding, homogeneous 100 degrees, and coming out of the last inductor, the difference between ID and OD is 200 degrees. Here comes homogeneous at 100, and comes out at 900 as a minimum with this difference between ID and OD. All right, this will require a few steps of thinking, so it's more complex than all the previous exercises. So will give us opportunity to discuss more things. This is a longer exercise. I'm going to wait for the full 5 minutes for the poll to happen. And please take a stab at it. Worst that can happen is you anonymously click a random letter. But we'll do this in the plant. All right. The poll is over, and let me share the results with you. And we are rocking here. So all of us chose the answer in this case is not so arguable. If you want a given increase in temperature, you need so much power, and we all agree on the right number. And essentially, it's a little bit of plug and chug. However, I wanted to bring up a subtlety that is in this exercise that will be important to calculate temperature in the ID and the OD because it's different. So when we said the minimum temperature at the seam is 900 degrees C, right? And I mentioned, I'm saying magically we have a 200-degree inhomogeneity, right? Difference 200 degrees, and we have formulas for calculating that one too. So what this means is that if the minimum temperature anywhere in the seam is 900 degrees, that means in the ID, in the inner part of the seam, is 900 degrees. That's the coldest part. If I have a 200-degree, let's get my laser pointer here. If I get a 200-degree temperature difference between inside and outside, that means that the outside will be at 1100 degrees C, 900 inside, 1100 outside, and then the average temperature would be approximately 1000 degrees. I cannot say it enough times. Do not think that these formulas are given by God and they are not perfect, but they help us think, and they help us think about what is inside, the temperature inside, what is the temperature outside, what could be an average temperature. And these things will come up in the final, right? So that's why I wanted to highlight this part here. And if we do now the plug and chug, we have the 5, here we have the wall thickness, here we have the width of the temperate zone, here we have the velocity in meters per second, here we have the 1000 degrees in average out of at the place of the peak temperature. 100 degrees that we said coming from the welding cage is more or less homogeneous through the seam, and it's more or less 455 kilowatts, as all of you correctly calculated. So we're doing great. Now, a little bit of context. This is a total for all inductors. But this amount that we calculated, and it cannot be all that far, is 23% of the maximum power, the nominal power. And we have 4 inductors of 500 kilowatts each. So this, what we calculated, is 23% of total power. So let's remember that we have issues of coupling, and what we read in the panel of the machine is the amount of current and voltage the machine is giving us. But the panel does not know how much of that is actually going into the tube. There might be technologies that give us that, and that's something we have discussed when I visited the Hickman plant a few weeks ago. All right, let's keep moving. Another thing that that I want to bring up that was I think I want to clarify over what we had in the videos you have watched is the exit temperature from the inductor. Using the equation for minimum inductor power, you get it straight out. But I wanted to spell it out clearly for you because I think it's an important parameter. So we have here the hot temperature that we know now is the average temperature exiting the inductor we consider. And Tc, in this case, is the average temperature entering the inductor being considered. Again, this is not the quench temperature. This is what comes, here we have what comes out. This is what came in. And this is how the heat we put in plays a role. So we have the power of the inductor that we consider. For example, in the case of the Hickman mill, we have 500 kilowatts. We have wall thickness, width of the temperate zone, and mill speed. So using this formula, and I'm not going to poll you on this one now, but using this formula, you can calculate the exit temperature from the inductor as an average. If you can also calculate the temperature differences between internal and external, using the considerations we discussed in the previous slide, you can calculate the temperature in the ID, the temperature in the OD, the average temperature. It's so much you can do having an educated insight as we're doing here. So where does this inhomogeneity, these temperature differences between inside and outside of the bead, right? And we already mentioned that there is this electrical component in which the temperature differences depends on volumetric heating. Volumetric heating depends on the magnetic field squared, and the magnetic fields themselves depend on the square of the distance to the pole, right? And this is an upper bound. Again, these are approximation, and this approximation is valid when we have an electrical reference depth bigger than the wall thickness. But this formula that is we have already discussed with much better graphics in the online course, right? Says that the temperature in the OD minus the temperature of the ID, this is the difference in temperatures between this point here outside and inside, is related to the average temperature coming out and the average temperature coming in. This is related to the power we're putting in, and related to this is radius, this distance ROD, it's not clear here, but it's ROD is from here to here, from the pole to the OD, divided the distance from the pole to the ID, right, and raised to the fourth power, because it was twice a square. So this formula, which is a very big approximation, gives us a sense of what role does the gap play, what role does the width of the temperate zone help us think that the poles of the inductors, when we buy the inductors, we seldom ask these questions to the supplier. But sometimes it might be good to have this in mind to make sure we don't have an inductor that is either too narrow or too wide for the diameter we need. So here we have an example calculation which we have seen in the online course. And I don't want people to start doing very long calculations, so I spelled it out myself. This is the ROD, and we are using Pythagoras, like the triangle trig, to calculate this distance as the gap squared plus the half width of the pole squared. And the ID distance would be the gap plus the thickness, all these, plus the half width of the pole squared. And with those two, we get these two distances. And if we know the average temperature coming in and the average temperature coming out, then we can calculate the temperature of inhomogeneity. And if we assume that this difference is split evenly around the average, what this means is that at the hot part, we split this in two, and we would have outside 1060 degrees, and inside we would have 940 degrees. Because this difference, we can say, splits evenly around the average that was given in this case as a fact. This is in line with what we discussed in the previous slide of minimum inductor power. So being under an inductor heats up our tube, but heats it up unevenly. How do we try to even out the temperature? Evening the temperatures is very important, because otherwise we can overheat the outside. We can have coarsening problems. We can even reach melting if we do it really bad. And or conversely, on the outside we can have the right temperature, and that's what we're measuring, and we're all happy. And in the inside, we have not reached full austenization. If we do not reach full austenization, we're not completely erasing all the bad microstructure that came from welding. Welding has a very fast cooling rate and is full of hard faces. So the space between the two inductors plays this very important role of letting the temperature homogenize across the thickness without putting any more heat there. So on the outside, we see that it cools down. On the inside, sometimes it can heat up, or can it be even or cool down, but much more slowly. And it's the hot outside of the bead of the seam transmits heat to the cold inside of the seam. And the time at which this takes place, this process is captured in this formula we have here. And it says that the temperature difference, right, and entering the next inductor, that means after homogenization, after this thermal homogenization, is more or less, and actually this formula is a pretty good one, it's more or less as the temperature difference you have coming out of the previous inductor. So coming out of an inductor, we have a pretty big temperature difference due to electrical reasons. And this smooths out in an exponential form. And what do we see here? We see that the longer the tube, the more homogeneous will be. Because of course, for a given mill speed, the longer the distance between inductors, the more time it will have to homogenize. Conversely, the higher the velocity, that will mean less residence time between the inductors, and will give us less homogenization. And here we have the wall thickness of the tube that goes square, which means wall thickness is a much important parameter than mill speed or length. What this means is if we increase our, we're dealing with a tube wall that is 20%, 10% thicker than a previous product, the consequences of homogenization would be as if I had changed the mill speed by a factor of 20%. So if I have a 10% thicker tube, all things being equal, I would need to reduce the mill speed by 20%. And so let's have a poll addressing this. Let me load it here. So let's estimate the temperature difference between outer and inner seam for entering the fourth inductor in the Hickman mill number 6. The Hickman mill number 6 is the one, the fourth inductor in this mill is the last one that gives us the peak temperature. So this temperature difference is extremely important because we need to know it to assess errors in to have a safety of margin on what our pyrometer tells us, because the pyrometer measures only the outside. So let's consider a tube of 9.5 millimeters and a mill speed of 38 meters per minute. All these are realistic numbers of a product that we make. Let's say that the distance between the exit of inductor 3 and the entry of inductor 4 is 0.8 meters. And let's assume that the temperature difference coming out of the inductor 3 is 100 degrees C. So what do you think is going to be the temperature difference coming into inductor 4. I'm going to put the formula back here. Oh, I hear that the poll is not showing, which is interesting. I'm going to close it and open it again. So does anybody see the poll, or nobody sees it? The poll has been up for a while now, but huh, huh. So nobody sees this poll. Let's see. Let's see what could have happened here. I'm going to close poll, edit questions. Okay. I am going to open it up again. And so, I see people are not seeing the poll. Maybe Carla. Yes.
Patricio,
Yes.
I'm seeing it, but what I was telling you is that have you opened it?
Yes, it's open.
Okay, so why don't you try uploading it again one more time?
I just did. How about if we briefly turn over the control to you and you upload it? I uploaded it twice and even edited it.
Okay.
I'll close what I have here.
Just 1 second, please. Okay, now it is there. Okay, Patricio, I give back to you the... I know, I need to close there. So I keep it.
Okay, so does everybody see it now, or? Okay. So I don't know if you guys are seeing it or not. I was scared that nobody could answer this one before.
We have 1 minute past, and no one has answered yet. Okay.
Okay, great.
Thanks for the one that started answering.
All right, excellent. So thank you very much, Carla, for doing this thing. I don't know what happened with let's see. I don't know what had happened with that question, but the good news is that yet again we everybody got it right, as you get to see. So let's think. First of all, if we were coming in with a temperature difference of let's see, my laser. If we were coming in with a difference of 100 degrees C, for sure we cannot increase the temperature in a difference when we are homogenizing. So C is not for sure. Between 13 and 43, we needed to do the numbers. And if we, this part here was 100 degrees, and we have all the information for length, for wall thickness, and for mill speed, we just plug and chug in this case, and we get this 43 degrees difference. So I'm really glad to see that everybody calculated it right, and it might seem a simple formula, but these things help us think quite a bit. All right, let's move on. I'm going to skip about the separation between inductors because we have a few minutes left. But the separation between inductors refer to what would be ideal to have, or what would be good enough to have. And typically in our mills, we have it something in between. About cooling in seam treatment, before I get to discuss this, because we have a few minutes left and we might not be able to do it completely. If you guys have any questions that in particular that you'd like to address in these last 10 minutes we have, you can send them to me or to everybody through the chat, and I'll try to address it directly and live now. And if not, you can always use the system from that we have for collaborations in the website. So, oops. So I'm going to skip on this poll about how that heat transfer differs during induction heating and air cooling. It would be great to have you think a little bit about it, but I'll try to cover some more material instead. So between the inductors, what I mean, as we are under the inductors or between inductors, the heat. What the problem we need to worry about is how the heat moves from the hot outside to the colder inside. So from the moment we leave welding to the moment we reach peak temperature, this is the heat mechanism that we worry about. Now, during the air cooling, the story changes, and what we need to worry about is how the heat goes from a relatively homogeneous seam to the outside of the tube, that through the periphery of the tube. That's something we have discussed, and we have these issues of convective cooling and radiation. So what I wanted to discuss now is how do we make sense of this quench temperature, TC. Now, with my apologies again, by this TC, I mean the temperature at which we get into the case. I'm not talking about the cold temperature entering an inductor. So we have a formula for that, and it's based on a well-known analysis that is done for welding, and it says that the temperature at which we reach quench is the temperature at which this intermediate temperature that I'm going to address in a minute, and a formula that involves the total power of all inductors together, the wall thickness, and the square root of mill speed and length of the air cooling stage. In this formula, the most important part is here in this TI, that is intermediate temperature. So this is the one for which Deborah Tiepo was asking me questions. And this intermediate temperature is the temperature at which the tube far from the seam is. So let's call it the side opposite to where the seam is. If we say that the seam is at 12 o'clock in a cross section, this TI would represent the temperature at the 6 o'clock. And this temperature depends on the diameter of the tube. Smaller tubes start with a fairly high TI, and big diameter tubes, TI is very close to room temperature. And because the tube loses heat by convection and radiation, so the 6 o'clock position in the tube is reduced as we move in the air cooling line. For big diameter tubes, it doesn't move much. It's always close to room temperature. For small diameter tubes, it can be relatively high. So what I like to do, and this might be our parting shot for today, and it can continue with the collaboration tools in the website. How about if we have a poll and we calculate this quench, the temperature at which we reach quench. This type of question is important in practice, and it's related to what you're going to see in the final. So this is an opportunity of doing it together here. All right, I will close the poll to discuss the results and wrap up for today. So as I share the answers with you, in this case, again, there is a correct answer, that is 415, what means I feel very safe putting pressure on Tenaris too. You guys, every time I have brought up these quantitative questions, you were almost all on the money for these values, and it's important to keep in mind that although these equations are not perfect, something so simple cannot possibly capture reality in all its richness, but help us think and help us get a ballpark of what we should expect. So this temperature you have just calculated is given a process. What temperature do we think we are entering the quenching cage? And if we wanted to change that temperature, for example, for increasing it, we could increase the heat of the inductors. If somebody asks us, how about having a new product with different wall thickness, we would know what to expect, and we would know how to make sense of changes in mill speed. Typically, there is very little we can do about the air cooling length. So let's see. So on this note, I think would be good to stop. If you have any more questions, please bring them up. I can tell you that I truly enjoyed this course, and this webinar has been interactive and fantastic in hearing your thoughts, your opinions, the chat, and seeing how you almost always had the right thoughts and the right answer. So I want to tell you again, this was a happy time, and I hope to see you again, either live or in some other opportunity. Thanks.